Hello everyone and welcome to the next module in this TensorFlow course. So what we're going to be doing here is talking about deep computer vision, which is very exciting, very cool. This has been used for all kinds of things. You ever seen the self-driving cars? For example, Tesla, they actually use a TensorFlow deep learning model, obviously very complicated, more than I can really explain here, to do a lot of their computer vision for self-driving. We've used computer vision in the medicine field. Computer vision is actually used in sports a lot for things like goal line technology and even detecting images and players on the field, doing analysis. There's lots of cool things they're doing with it nowadays. And for our purposes, what we're going to be doing is using this to perform classification, although it can be used for object detection and recognition, as well as facial detection and recognition as well. So all kinds of applications. In my opinion, one of the cooler things in deep learning that we're doing right now. And let's go ahead and talk about what we're actually going to be focusing on here. So we're going to start by discussing what a convolutional neural network is, which is essentially the way that we do deep learning. We're going to learn about image data. So what's the difference between image data and other regular data? We're going to talk about convolutional layers and pooling layers and how stacks of those work together as what we call a convolutional base for our convolutional neural network. And we're going to talk about CNN architectures and get into actually using pre-trained models that have been developed by companies such as Google and TensorFlow themselves to perform classification tasks for us. So that is pretty much the breakdown of what we're about to learn. There's quite a bit in this module. It's probably the more difficult one, or the most difficult one we've been doing so far. So if you do get lost at any point or you don't understand some of it, don't feel bad. This stuff is very difficult, and I would obviously recommend reading through some of the descriptions I have here in this notebook, which again you can find from the link in the description, or looking up some things that maybe I don't go into enough depth about in your own time, as I can't really spend 10 11 hours explaining a convolutional neural network. So let's now talk about image data, which is the first thing we need to understand. So in our previous examples, what we did when we had a neural network is we had two-dimensional data, right? We had a width and a height when we were trying to classify some kind of images using a dense neural network. And well, that's what we use, 2 dimensions. Well, with an image, we actually have 3 dimensions. And what makes up those dimensions? Well, we have a height and we have a width, and then we have something called color channels. Now, it's very important to understand this because we're going to see this a lot as we get into convolutional networks, that the same image is really represented by 3 specific layers, right? We have the first layer, which tells us all of the red values of the pixels, the second layer, which tells us all the green values, and the third layer, which tells us all the blue values. So in this case, those are the color channels, and we're going to be talking about channels in depth quite a bit in this series. So just understand that although you think of an image as a 2-dimensional kind of thing, in our computer, it's really represented by 3 dimensions, where these channels are telling us the color of each pixel. Because remember, in red, green, blue, you have 3 values for each pixel, which means that you're going to need 3 layers to represent that pixel, right? So this is what we can kind of think of it as, a stack of layers, and in this case, a stack of pixels, right? Or a stack of colors, really, telling us the value for each pixel. So if we were to draw this to the screen, we would get the blue, green, and red values of each pixel, determine the color of it, and then draw the 2-dimensional image, right? Based on the width and the height. Okay, so now we're going to talk about a convolutional neural network and the difference between that and a dense neural network. So in our previous examples, when we used a dense neural network to do some kind of image classification like that fashion MNIST dataset, what it essentially did was look at the entire image at once and determined, based on finding features in specific areas of the image, what that image was, right? Maybe it found an edge here, a line here, maybe it found a shape, maybe it found a horizontal diagonal line. The important thing to understand, though, is that when it found these patterns and learned the patterns that made up specific shapes, it learned them in specific areas. It knew that if we're in between, for example, looking at this cat image, and we're going to classify this as a cat, if an eye exists on, the left side of the screen where the eyes are here, then that's a cat. It doesn't necessarily know that if we flipped this cat, we did a horizontal flip of this cat, and the eyes were over here, that is a pattern that makes up a cat. So the idea is that the dense network looks at things globally. It looks at the entire image and learns patterns in specific areas. That's why we need things to be centered. We need things to be very similar when we use a dense neural network to actually perform image classification, because it cannot learn local patterns and apply those to different areas of the image. So for example, some patterns we might look for when we're looking at an image like a cat here would be something like this, right? We would hope that maybe we could find a few ears, we could find the eyes, the nose, and the paws here, and those features would tell us that this makes up a cat. Now with a dense neural network, it would find these features, it would learn them, learn these patterns. It would only learn them in this specific area where they're boxed off, which means if I horizontally flip this image, right, and I go like that, then it's not going to know that that's a cat because it learned that pattern in a specific area. It'll need to relearn that pattern in the other area. Now, a convolutional neural network, on the other hand, learns local patterns. So rather than learning that the ear exists in, this specific location, it just learns that this is what an ear looks like, and it can find that anywhere in the image. And we'll talk about how we do that as we get to the explanation, but the whole point is that our convolutional neural network will scan through our entire image. It will pick up features and find features in the image. And then based on the features that exist in that image, we'll pass that actually to a dense neural network or a dense classifier. It will look at the presence of these features and determine, the combination of these presences of features that make up specific classes or make up specific objects. So that's kind of the point. I hope that makes sense. The main thing to remember is that dense neural networks work on a global scale, meaning they learn global patterns which are found in specific areas, whereas convolutional neural networks or convolutional layers will find patterns that exist anywhere in the image because they know what the pattern looks like, not that it just exists in a specific area. All right, so how they work, right? So let's see when a neural network, regular neural network, looks at this dog image. This is a good example. I should have been using this before. It will find that there's two eyes that exist here, right? And it'll say, okay, so I found that these eyes make up a dog. This is its training image, for example, and it's like, okay, so this pattern makes up the dog, the eye is in this location. Now, what happens when we do this? And we flip the image to the other side. Well, our neural network starts looking for these eyes, right, on the left side of the image where it found them previously and where it was trained on. It obviously doesn't find them there, and so it says that our image isn't a dog. Although it clearly is a dog, it's just a dog that's orientated differently. In fact, it's just flipped horizontally, right? Or actually, I guess I would say vertically, flipped vertically. So since it doesn't find the eyes in this location, and it can only look at patterns that it's learned in specific locations, it knows that this, or it's going to say this isn't a dog, even though it is. Whereas our convolutional layer will find the eyes regardless of where they are in the image and still tell us that this is a dog, because even though the dog's moved over, it knows what an eye looks like, so it can find the eye anywhere in the image. So that's kind of the point of the convolutional neural network and the convolutional layer. And what the convolutional layer does is look at our image and essentially feed back to us what we call an output feature map that tells us about the presence of specific features, or what we're going to call filters, in our image. So that is kind of the way that works. Now, essentially, the thing we have to remember is that our dense neural networks output just a bunch of numeric values, whereas what our convolutional layers are actually going to be doing is outputting what we call a feature map. Now, I'm going to scroll down here to show you this example. What we're actually going to do is run what we call a filter over our image. We're going to sample the image at all these different areas, and then we're going to create what we call an output feature map that quantifies the presence of the filters patterned at different locations. And we'll run many, many, many different filters over our image at a time, so that we have all these different feature maps telling us about the presence of all these different features. So one convolutional layer will start by doing that with very small, simple filters, such as straight lines like this, and then other convolutional layers on top of that, right? Because it's going to return a map that looks something like this out of the layer. We'll take this map in now, the one that was created from the previous layer, and say, okay, well, if this map is representing to me, for example, the presence of these diagonal lines, let me try to look for curves, right? Or let me try to look for edges. So it will look at the presence of the features from the previous convolutional layer and then say, okay, well, if I have all these lines combined together, that makes up an edge, and it will look for that, right? And that's kind of the way that a convolutional neural network works and why we stack these different layers. Now, we also use something called pooling, and there's a few other things that we're going to get into, but that is the basics. I'm going to go into a drawing example and show you exactly how that works, but hopefully this makes a little bit of sense that the convolutional layer returns a feature map that quantifies the presence of a filter at a specific location. And this filter, the advantage of it is that we slide it across the entire image, so if this filter or this feature is present anywhere in the image, we will know about it, rather than in our dense network where it had to learn that pattern in a specific global location. Okay, so let's get on the drawing tablet and do a few examples. All right, so I'm here on my drawing tablet, and we're going to explain exactly how a convolutional layer works and how the network kind of works together. So this is an image I've drawn on the left side of our screen here. I know this is very basic, this is just an X, right? This is what our image is. We're just going to assume this is grayscale. We're going to avoid doing anything with color channels this second just because they're not that important, but just understand that what I'm about to show you does apply to color channels as well and to multiple kind of layers and depth. And then if we can understand it on a simple level, we should be able to understand it more thoroughly. So what we want essentially is our convolutional layer to give us some output that's meaningful about this image. So we're going to assume this is the first convolutional layer, and what it needs to do essentially is return to us some feature map that tells us about the presence of specific what we call filters in this image. So each convolutional layer has a few properties to it. The first one is going to be the input size. So what can we expect? Wow, what is that? That was as the as the input size. How many filters are we going to have? So filters like this. And what's the sample size of our filters? That's what we need to know for each of our convolutional neural networks. So essentially, what is a filter? Well, a filter is just some pattern of pixels, and we saw them before. We'll do a pretty basic one here as the filter we're going to look for, which will look something like this. This will be the first filter we're going to look for just to illustrate how this works. But the idea is that at each convolutional layer, we look for many different filters. And in fact, the number we're typically looking for is actually about times 32 filters. Sometimes we have 64 filters as well, and sometimes even 128. So we can do as many filters as we want, as few filters as we want, but the filters are what is going to be trained. So this filter is actually what is going to be found by the neural network. It's what's going to change. It's, this is essentially what we're looking for. This is what's created in the program. And that's kind of like the trainable parameter of a convolutional neural network is the filter. So the amount of filters and what they are will change as the program goes on, as we're learning more and figuring out what features that make up, a specific image. So I'm going to get rid of this stuff right now, just so we can draw and do a basic example. But I want to show you how we look for a filter in the image. So we have filters, right? They'll come up with them. They're going to start completely random, but they'll change as we go on. So let's say the filter we're looking for is that one I drew before. I'm just going to redraw it at the top here a little bit smaller. And we'll just say it's a diagonal line, right? But another filter we could look for might be something like, a straight line, just like that, all across. We could have a horizontal line, and in fact, we'll have 32 of them. And when we're doing just, 3x3 grids of filters, well, there's not that many, combinations we're going to do, at least grayscale wise. So what we'll do is we'll define the sample size, which is how big our filter is going to be 3x3, which we know right now, which means that what we're going to do is we're going to look at 3x3 spots in our image and look at the pixels and try to find how closely these filters match with the pixels we're looking at on each sample. So what this is going to do, this convolutional layer, is going to output to us what we call a feature map, which is going to be a little bit smaller than the original image, and you'll see why in a second, but that tells us about the presence of specific features in areas of the image. So since we're looking for two filters here, actually we'll do two filters, which means that we're actually going to have a depth 2 feature map being returned to us, right? Because for two filters, that means we need two maps quantifying the presence of both of those filters. So for this green box that we're looking on the left side here, we'll look for this first filter here. And what do we get? Well, the way we actually do this, the way we look at this filter, is we take the cross product, or actually not the cross product, the dot product, sorry, between this little green box and this filter, right? Because they're both pixels, they're both actually numeric values down at the bottom. So what we do is we take that dot product, which essentially means we're element-wise adding, or what is it, element-wise multiplying all of these pixels by each other. So if this pixel value is 0, right, because it's white, or it could be the other way around, we could say white is 1, black is 0, it doesn't really matter, right? If this is a 0 and this is a 1, these are obviously very different. And when we do the dot product of those two, so we multiply them together, then in our output feature, we would have a 0, right? That's kind of the way it works. So we do this dot product of this entire thing. If you don't know what the dot product is, I'm not really going to go into that. But we do the dot product, and that gives us some value, essentially telling us how similar these two blocks are. So how similar this sample is that we're taking of the image and the filter that we're looking for. If they're very similar, we're going to likely put a 1 or something telling us, you know, they're very close together. If they're not similar at all, we're going to put a 0. So in this case, for our first filter, we're probably going to have a value because this middle pixel is the same of something like 0.12, right? But all the other values are different, so it's not going to be very similar whatsoever. So then what we're going to do now is we'll look at the actually second filter, which is this horizontal line. And in fact, we're going to get a very similar output response here, probably something like, you know, 0.12. That's going to go in the top left. And again, these are both maps representing each filter, right? So now we'll move our green box over 1 like this. So just shift that over 1. And now we'll start looking at the next section. And in fact, I'm going to see if I can erase this just to make it a little bit cleaner here. Get rid of the green. There we go. Okay. So we'll move this box over like this. And now we'll start looking at this one. And we'll do the exact same thing we did again before. So we're going to say, all right, how similar are these? Well, they're not similar at all. So we're going to get a 0 for that first filter. How similar are the other ones? Oh, actually, they're like a little bit similar. There's a lot of white that's kind of in the same space, like, you know, stuff like that. So we'll say maybe this is like 0.7, right? And I'm just randomly picking these numbers. They are going to be much different than what I'm putting in here, but I'm just trying to get you to understand what's kind of happening, right? And this is completely random the way I'm making the numbers. So just make sure you understand that, because this is not exactly what it would look like. Okay, so then we're going to move the box over one more time. Let's just erase this to keep this clean. This will be the last time we do this for the purpose of this example. And now what we're going to have is, wow, we have a perfect match for the first filter. So we put 1. The other one's like, it's kind of similar. There's a few things that are different. So maybe this gets like a 0.4 or something, right? Whatever they are, we end up getting some values. So we'll fill in all these values. Let's just put some arbitrary values here for now, just so we can do something with the example. 0.7, 0, 0.12, 0.42, 0.3, 0.9, 0.1. Again, completely random, 0.4, 0.6. All right, so this is now what we've gotten, our response map from looking at 2 filters on our original image of 5 by 5. Now notice that the size of these is 3 by 3, and obviously the reason for that is because in a 5 by 5 image, when we're taking 3 by 3 samples, well, we can only take 9 3 by 3 samples, because when we go down a row, right, we're going to move down 1, and we're going to do the same thing we did before of these 3 by 3 samples. And if we add the amount of times we can do that, well, we just get 3 by 3, which is 9. So this now is kind of telling us of the presence of features in this original image map. Now, the thing is, though, we're going to do this 64 times, right? For 64 filters or 32 filters, or the amount of filters that we have. So we're going to have a lot of layers, like a ton of different layers, which means that we're going to be constantly expanding as we go through the convolutional layers, the depth of this kind of output feature map. And that means that there's a lot of computations that need to be done, and essentially that means that this can be very slow. So now we need to talk about an operation called pooling. So I'll backtrack a little bit, but we will talk about pooling in a second. What's going to happen, right, is when we have all these layers that are generated, so this is called the output feature map, right, from this original image, what we're going to do is the next convolutional layer in the network is now going to do the process we just talked about, except on this output feature map, which means that since this one was picking up things like lines and edges, right, the next convolutional layer will pick up combinations of lines and edges and maybe find what a curve is, right? We'll slowly work our way up from very, very small amount of pixels to finding more and more, almost I want to say abstract different features that exist in the image. And this is what really allows us to do some amazing things with a convolutional neural network. When we have a ton of different layers stacking up on each other, we can pick out all the small little edges, which are pretty easy to find. And with all these combinations of layers working together, we can even find things like, say, eyes, right? Or feet, or heads, or face, right? We can find very complicated structures because we slowly work our way up, starting by solving very easy problems, which are like finding lines, and then finding combinations of lines, combination of edges, shapes, and like very abstract things. That's how this convolutional network works. So we've done that now. It's now time to talk about pooling. And we'll also talk about actually we'll go padding first before we go pooling. It doesn't really matter what order we talk about this in, but I just think padding makes sense based on the way we're going right now. So sometimes we want to make sure that the output feature map from our original image here is the same dimensions or same size as this, right? So this is 5 by 5, obviously, and this is 3 by 3. So if we want this to be 5 by 5 as an output, what we need to do is add something called padding to our original image. So padding is essentially just adding an extra row and column on each side of our image here, so that when we just fill in all these pixels in like kind of the padded pixels here as just blank, like random pixels, they don't mean anything. Essentially why we do that is so that when we do our 3x3 sample size here like this, we can take a 3x3 sample where every single pixel is in the center of that sample. Because right now, this pixel is not in the center, this pixel can never be in the center, this pixel can never be in the center, only, a few pixels get to be in the center. And what this allows us to do is generate an output map that is the same size as our original input and allows us to look at features that are maybe right on the edges of images that we might not have been able to see before. Now, this isn't super important when you go to like very large images, but it's just something to consider. You can add padding. We may do this as we get through our examples. And there's also something called stride, which I want to talk about as well. So what a stride is essentially how much we move this sample box every time that we're about to move it, right? So before, so let's say we're doing an example with padding here, right? Our first sample we would take here, and again, these pixels are just added. We added them in to make this work better for us. You would assume that the next time we move the box, we're going to move it 1 pixel over. That's called a stride of 1. We can do that, but we also can employ a stride of 2, which means we'll move over by 2. Obviously, the larger your stride, the smaller your output feature map is going to be, so you might want to add more padding. Well, you don't want to add too much padding, but it's just something to consider, and we will use a stride in different instances. Okay, so that's great. That hopefully makes sense. Let's erase this now. We don't need this anymore. We talked about padding. We talked about the stride. And now we're going to talk about a pooling operation, which is very important. So kind of the idea is that we're going to have a ton of layers, right, for all these filters, and we're just going to have a lot of numbers, a lot of computations, and there must be some way to make these a little bit simpler, a little bit easier to use. Well, yes, that's true, and there is a way to do that, and that's called pooling. So there's 3 different types of pooling. Well, there is more, but the basic ones are min, max, and average. And essentially a pooling operation is just taking specific values from a sample of the output feature map. So once we generate this output feature map, what we do to reduce its dimensionality and just make it a little bit easier to work with is what we sample typically 2x2 areas of this output feature map and just take either the min, max, or average value of all the values inside of here and map these. So we're going to go back this way to a new feature map that's twice, 1 times this size essentially. Or not, what am I saying? 2 times smaller than this original map. Now it's kind of hard with 3x3 to really show you this, but essentially what's going to end up happening is we're going to have something like this. So we're going to take the sample here. We're going to say, okay, what are we doing? Min, max, or average pooling? If we're doing min pooling, we're going to take the smallest value, which means we'll take 0. If we're doing max pooling, we'll take the maximum value, which means we'll take 0.3. If we're doing average, we're probably going to get an average value of close to what? 0.2 maybe? So let's say 0.2. We'll go there. That's how we do that with pooling. Again, just to make this feature map smaller. So we'll do that for both of the filters, but let's just say this is 0.2. Let's say this here that I'm blocking off is, I don't know, what is this going to be? 0.6. It's hard to do this average with 4 numbers. Let's say this one down here is going to be 0. I don't know, let's just do 2.1 or something. And then this last one here, we got some bigger values. Maybe this will be like 0.4. Okay, so that's one. The one down here will have some values of its own. We'll just do squiggles to represent that it has something. And we've effectively done a max pooling operation on this. We've reduced the size of it by about half. And that is kind of how that works. Now, typically what we do is we use a 2x2 pooling or like sample size like that with the stride of 2, which actually means that we would draw it like this. But since we're not going to do padding on this layer right now, we'll just do a stride of 1. And this is how we pool it. Now, the different kinds of pooling are used for different kind of things. The reason we would use a max pooling operation is to pretty much tell us about the maximum presence of a feature in that kind of local area. We really only care if the feature exists, or if it doesn't exist. And average pooling is not very often used, although in this case we did use an average pooling. But, it's just different kinds of pooling. An average tells you about the average presence of the feature in that area. Max tells you about, is that feature present in that area at all? And min tells you, does it not exist? If it doesn't exist, right, we're just going to have a 0 if there's even 1 0 in that area. So that's the point of pooling, That's the point of convolutional layers. I think I'm done with the whiteboarding for now. We're actually going to start getting into a little bit of code and talking about creating our own convolutional networks, which hopefully will make this a lot more clear. So let's go ahead and get into that. Alright, so now it is time to create our first convolutional neural network. Now we're going to be using Keras to do this, and we're also going to be using the CIFAR image dataset that contains 60,000 images of 10 different classes of everyday objects. Now these images are 32 by 32, which essentially means they are blurs, and they are colorful. Now, I just want to emphasize as we get into this that the reason I'm not typing all of these lines out and that I just have them in here already is because this is likely what you guys will be using or doing when you actually make your own models. Chances are that you are not going to sit, unless you're a pro at TensorFlow, and I am not even there yet either with my knowledge of it, and have all of the lines memorized and not have to go reference the syntax. So the point is here, so long as you can understand why this works and what these lines are doing, you're going to be fine. You don't need to memorize them, and I have not memorized them, and I don't. I look up the documentation, I copy and paste what I need, I alter them, I write a little bit of my own code, but that's kind of what you're going to end up doing, so that's what I'm doing here. So this is the image dataset. We have truck, horse, ship, airplane, just some everyday regular objects. There is 60,000 images, as we said, and 6,000 images of each class. So we don't have too many images of just one specific class. So we'll start by importing our modules. So TensorFlow, we're going to import tensorflow.keras. We're going to use the dataset built into Keras for this. So that's the CIFAR image dataset, which you can actually look at just by clicking at this. It'll bring you and give the information about the dataset. Although we don't need that right now because I already know the information about it. And now we're just going to load our images in. So again, this stuff, the way this works is you're going to say datasets.cifar10.load_data. Now this loads it in as like a very strange TensorFlow object that's like a dataset object. So this is different from what we've used before, where some of our objects have actually been like in NumPy arrays where we can look at them better. This is not going to be in that, so just something to keep in mind here. And we're going to normalize this data into train images and test images by just dividing both of them by 255. Now again, we're doing that because we want to make sure that our values are between 0 and 1, because that's just a lot better to work with in our neural networks rather than large integer values. It just causes, some things to mess up sometimes. Now class names, we're just going to define a list here so we have all the class names, so that 0 represents airplane, 1 automobile so far until truck. We'll run that block of code here. We'll download this dataset, although I don't think it takes that long to do that. So, okay, so wait, I guess that's good. I think we're okay there. And now let's just have a look at actually some of the images here by running this script. So we can see this is a truck. I can change the image index to be 2. We can see this is another truck. Let's go to say 6. We get a bird. And you can see these are really blurry, but that's fine for this example. We're just trying to get something that works all right. Okay, so that's a horse. You get the point. All right, so now CNN architecture. So essentially, we've already talked about how a convolutional neural network works. We haven't talked about the architecture and how we actually make one. Essentially, what we do is we stack a bunch of convolutional layers and max pooling, min pooling, or average pooling layers together in something like this, right? So after each convolutional layer, we have a max pooling layer, some kind of pooling layer typically to reduce the dimensionality, although you don't need that. You could just go straight into 3 convolutional layers. And on our first layer, what we do is we define the amount of filters, just like here. We define the sample size, so how big are those filters. An activation function, which essentially means after we apply that, that dot product operation that we talked about, we'll apply rectifier linear unit to that and then put that in the output feature map. Again, we've talked about activations functions before, so I won't go too far into depth with them. And then we define the input shape, which essentially means what can we expect in this first layer? Well, 32 by 32 by 3. These ones, we don't need to do that because they're going to figure out what that is based on the input from the previous layer. All right, so these are just a breakdown of the layers. The convolution or the max pooling layers here, 2 by 2 essentially means that what we're going to do is we're going to have a 2 by 2 sample size with actually a stride of 2. Again, the whole point of this is to actually divide or, shrink it by a factor of 2. how large each of these layers are. All right, so now let's have a summary. It's already printed out here. We can see that we have, oh, wait, is this correct? MobileNet v2. I don't think that's correct. That's because I haven't run this one. My apologies on that, guys. This is from something later in the tutorial. We can see that we have conv2d as our first layer. This is the output shape of that layer. Notice that it is not 32 by 32 by 32. It is 30 by 30 by 32 because when we do that sampling without padding, right, that's what we're going to get. We're going to get 2 pixels less because the amount of samples we can take. All right. Next, we have the max pooling 2D layer. So this now says the output shape is 15 by 15 by 32, which means we've shrunk this shape by a factor of 2. We do a convolution on this, which means that now we get 13, 13, and we're doing 64 because we're going to take 64 filters this time. And then a max pooling again, we go 6 by 6 by 64 because we're going to divide this again by a factor of 2. Notice that it just rounded, right? And then conv2d, so another layer here, we get 4 by 4 by 64, again because of the way we take those values. So this is what we've defined so far, but this is not the end of our convolutional neural network. In fact, this doesn't really mean much to us, right? This just tells us about the presence of specific features as we've gone through this convolution base, which is what this is called, the stack of convolution and max pooling layers. So what we actually need to do is now pass this information into some kind of dense layer classifier, which is actually going to take this pixel data that we've kind of calculated and found, so the almost extraction of features that exist in the image, and tell us which combination of these features map to either, you know, what one of these 10 classes are. So that's kind of the point. You do this convolution base, which extracts all of the features out of your image, and then you use the dense network to say, okay, well, if these combination of features exist, then that means this image is this, otherwise it's this and that, and so on. So that's what we're doing here. All right, so let's say adding the dense layers. So to add the dense layers, pretty easy. Model.add is just how we add them, right? So we're gonna flatten all of those pixels, which essentially means take the 4 by 4 by 64 and just put those all into a straight line like we've done before, so just one dimensional. Then we're going to have a 64 neuron dense layer that connects all of those things to it with an activation function of rectifier linear unit. Then our output layer of a dense layer with 10 neurons, obviously 10 because that's the amount of classes we have for this problem. So let's run this here. We'll add those layers. Let's look at a summary and see how things have changed now. So we go from 4 by 4 by 64 to 1024. Notice that that is precisely the calculation of 4 times 4 times 64. That's how we get that number here. Then we have a dense layer and another dense layer, and this is our output layer. Finally, this is what we're getting, is we're going to get 10 neurons out, so essentially just a list of values, and that's how we can determine which class is predicted. So this up to here is the convolutional base. This is what we call the classifier, and they work together to essentially extract the features and then look at the features and predict the actual object or whatever it is, the class. All right. So that's how that works. Now it's time to train. Again, we'll go through this quickly. I believe I've already trained this. This takes a long time to train, so I'm actually going to reduce the epochs here to just be 4. I'd recommend you guys train this on higher, so like 10 if you're going to do it, but it does take a while, so for our purposes and for my time, we'll leave it a little bit shorter right now, but you should be getting about a 70% accuracy, and you can see I've trained this previously if you train it on 10 epochs, but I'm just going to train it up to 4. We'll get our 67, 68%. And that should be fine, so we'll be back once this is trained, and then we'll talk about how some of this works. Okay, so the model is finally finished training. We did about 4 epochs. You can see we got an accuracy of about 67% on the evaluation data. To quickly go over this stuff, optimizer's Atom, we've talked about that before. Loss function is sparse categorical cross entropy. That one, I mean, you can read this if you want. Computes the cross entropy loss between the labels and predictions. And I'm not going to go into that, but these kind of things are things that you can look up if you really want to understand why they work. For most problems, you can just, if you want to figure out what, you know, loss function or optimizer to use, just use the basics. Like use Atom, use a categorical cross entropy. If you're using a classification task, you want to do something like this. There's just, you can go up and look kind of all of the different loss functions, and it'll tell you when to use which one, and you can kind of mess with them and tweak them if you want. Now, history equals model.fit. This is just so we can access some of the statistics from this. Model.fit obviously is just training the data to this test images, test labels, and train images and train labels, where this is the validation data. So evaluating the model, if we want to evaluate the model, we can evaluate it now on the test images and test labels. We're obviously going to get the same thing because the valuation is test images and test labels. So we should get the same accuracy as 67.35, which we do right here. All right, so there we go. We get about 70%. If you guys train this on 10 epochs, you should get close to 70. I'm a little bit lower just because I didn't want to go that high. And that is now the model. I mean, we could use this if we want. We could use predict. We could pass in some image and we could see the prediction for it. I'm not going to do that just because we've already talked about that enough, and I want to get into some of the cooler stuff when we're working with smaller data sets. So the basic idea here is this is actually a pretty small data set, right? We use about 60,000 images, and if you think about the amount of different patterns we need to pick up to classify, things like horses versus trucks, that's a pretty difficult task to do, which means that we need a lot of data. And in fact, some of the best convolutional neural networks that are out there are trained on millions of pieces of, sample information or of data. So obviously we don't have that kind of data. So how can we work with, a few images, maybe like a few thousand images, and still get a decent model? Well, the thing is, you can't unless we use some of the techniques that I'm about to show you. So working with small data sets. So just like I mentioned, it's difficult to create a very good convolutional neural network from scratch if you're using a small amount of data. That is why we can actually employ these techniques. The first one, data augmentation, but also using pre-trained models to kind of accomplish what we need to do. And that's what we're going to be talking about now in the second part of the tutorial. We're going to create another convolutional neural network. So just to clarify, this is created. We've made the model up here already. This is all we need to do it. This is the architecture, and this was just to get you familiar with the idea. So data augmentation. So this is basically the idea. If you have one image, we can turn that image into several different images and train and pass all those images to our model. So essentially, if we can rotate the image, if we can flip it, if we can stretch it, compress it, shift it, zoom it, whatever it is, and pass that to our model, it should be better at generalizing because we'll see the same image, but modified and augmented multiple times, which means that we can turn a data set, say, of 10,000 images into 40,000 images by doing 4 augmentations on every single image. Now, obviously, you still want a lot of unique images, but this technique can help a lot and is used quite a bit because that allows our kind of model to be able to pick up images that maybe are orientated differently or zoomed in a bit or stretched, something different, right? Just better at generalizing, which is the whole point. So I'm not going to go through this in too much depth, but this is essentially a script that does data augmentation for you. We're going to use this image data generator from the keras.preprocessing.image module. We're going to create an image data generator object. Now, essentially what this allows us to do is specify some parameters on how we want to modify our image. In this case, we have the rotation range, some shifts, shear, zoom, horizontal flip, and the mode. Now, I'm not going to go into how this works. You can look up the documentation if you'd like, but essentially this will just allow us to augment our images. Now, what I'm going to do is pick one arbitrary image from the test image dataset, or test image, I guess, group of photos, whatever you want to call it. I'm going to convert that to an image array, which essentially takes it from the weird dataset object that it kind of is and turns it into a NumPy array. Then we're going to reshape this so that it's in the form 1, which essentially means 1, and then this will figure out what the rest of the shape should be. 1, and then plus the image shape, which is whatever this shape is. So we'll reshape that. And then what we're going to do is we're going to say for batch in dataflow gen.flow. We'll talk about how that works in a second. Essentially, this is just going to augment the image for us and actually save it onto our drive. So in this instance, what's going to happen is this datagen.flow is going to take the image, which we've created here, right? And we formatted it correctly by doing these 2 steps, which you need to do beforehand. It's going to save this image as test.jpg, and this will be the prefix, which means there'll be some information after. And it will do this as many times until we break. So essentially, given an image, it will do test 1, test 2, test 3, test 4, test 5, with random augmentations using this until eventually we decide to break out of this. Now, what I'm doing is just showing the image by doing this, and batch 0 is just showing us the, that first image in there. And that's kind of how this works. So you can mess with this script and figure out a way to use it, but I would recommend if you want to do data augmentation, just look into image data generator. This is something that I just wanted to show you so you're aware of, and I'll just run it so you can see exactly how this works. So essentially, given an image of a truck, what it will do is augment it in these different ways. You can see kind of the shifts, the translations, the rotations, all of that. And we'll do actually a different image here to see what one looks like. Let's just do image, say 20. See if we get something different. So in this case, I believe this is maybe like a deer or a rabbit or a dog or something. I don't really know exactly what it is because it's so blurry, but you can see that's kind of the shifts we're getting, and it makes sense because you want to have images in different areas so that we have a better generalization. All right, so let's close that. Okay, so now we're gonna talk about using, pre-trained models. Okay, so we talked about data augmentation. That's a great technique if you want to increase the size of your data set, but what if even after that, we still don't have enough images in our data set? Well, what we can do is use something called a pre-trained model. Now, companies like Google and, TensorFlow, which is owned by Google, make their own amazing convolutional neural networks that are completely open source that we can use. So what we're going to do is actually use part of a convolutional neural network that they've trained already on, I believe, 1.4 million images. And we're just going to use part of that model as kind of the base of our model so that we have a really good starting point, and all we need to do is what's called fine-tune the last few layers of that network so that they work a little bit better for our purposes. So what we're going to do essentially is say, all right, we have this model that Google's trained. They've trained it on 1.4 million images. It's capable of classifying, let's say, 1,000 different classes, which is actually the example we'll look at later. So obviously the beginning of that model is what's picking up on the smaller edges and, kind of the very general things that appear in all of our images. So if we can use the base of that model, so kind of the beginning of it, that does a really good job picking up on edges and general things that will apply to any images, then what we can do is just change the top layers of that model a tiny bit or add our own layers to it to classify for the problem that we want. And that should be a very effective way to use this pre-trained model. We're saying we're going to use the beginning part that's really good at kind of the generalization step. Then we'll pass it into our own layers that will do whatever we need to do specifically for our problem. That's what's like the fine tuning step. And then we should have a model that works pretty well. And in fact, that's what we're going to do in this example now. So that's kind of the point of what I'm talking about here, is using part of a model that already exists that's very good at generalizing and it's been trained on so many different images. And then we'll pass our own training data in. We won't modify the beginning aspect of our neural network because it already works really well. We'll just modify the last few layers that are really good at classifying, for example, just cats and dogs, which is exactly the example we're actually going to do here. So I hope that makes sense. As we get through, this should be cleared up a little bit, but using a pre-trained model is now the section we're getting into. So this is based on this documentation. As always, I'm referencing everything so you guys can go see that if you'd like. We can do our imports like this. We're going to load a data set. This actually takes a second to load the data set, I believe. Oh, maybe not. And essentially the problem we're doing is trying to classify dogs versus cats with a fair degree of accuracy. In fact, we'd like to get above 90%. So this is the data set we're loading in from TensorFlow datasets as TFDS. This is kind of a weird way to load it in. Again, stuff like this, you just have to reference the documentation. I can explain it to you, but it's not really going to help when the next example is going to be a different way of loading the data, right? So long as you know how to get the data in the correct form, you can get it into some kind of NumPy array, you can split it into training, testing, and validation data, you should be okay. And if you're using a TensorFlow dataset, it should tell you in the documentation how to load it in properly. So we'll load it in here. We're training 80% train. We'll go 10% for, raw validation and 10% for the testing data. So we've loaded that. And now what we're doing here is just we're going to look at a few images. So this actually creates a function. I know this is a weird thing. This is pretty unique to this example that allows us to call this function with some integer essentially and get what the actual string representation of that is, so the label for it. And what I'm doing here is just taking two images from our raw training data set and just displaying them. And you can see that's what we're getting here, dog and dog. And if I go ahead and take 5, we'll see these are what our images look like. Right, so here's an example of a dog, we have a cat, right, and so on and so forth. You get the point there. Now, notice though that these images are different dimensions. In fact, none of these images, other than these two, actually are the same dimension at all. Oh, actually, I don't think these ones are either. So obviously, there's a step that we need to do, which is we need to scale all these images to be the same size. So to do that, what we're going to do is write a little function like this that essentially will return an image that is reshaped. So I guess that is reshaped to the image size, which I'm going to set at 160 by 160. Now we can make this bigger if we want, but the problem sometimes is if you make an image that is bigger than, like you want to make your image bigger than most of your dataset examples, and that means you're going to be really stretching a lot of the examples out and you're losing a lot of detail. So it's much better to make the image size smaller rather than bigger. You might say, well, if you make it smaller, you're going to lose detail too, but it's better to compress it smaller than it is to go really big. even just when it comes to the amount of training time and how complex the network is going to be. So anyways, that's something to consider. You can mess around with those when you're making your own networks, but again, smaller is typically better in my opinion. You don't want to go too small, but something that's like, you know, half the size of what an average image would be. All right, so we're going to go format example. So what we're going to do is take an image and a label, and what this will do is return to us just the reshaped image and label. So in this case, we're going to cast, which just means convert every single pixel in our image to be a float 32 value because it could be integers. We're then going to divide that by 127.5, which taken is exactly half of 255, and then subtract 1. Then we're going to resize this image to be the image size. So sorry, the image will be resized to the image size, so 160 by 160, and we'll return the new image and the label. So now we can apply this function to all of our images using map. If you don't know what map is, essentially it takes every single example in this case going to be raw train, and applies the function to it, which will mean that it will convert raw train into images that are all resized to 160 by 160, and we'll do the same thing for validation and test. So run that, no issue there. And now let's have a look at our images and see what we get. And there we are. Now I've just messed up the color because I didn't add a CMap thing, which I think I needed. Where was the CMap? Anyways, you know what? That's fine for now. This is what our images look like. This is the resize. Now we get all our images 160 by 160, and we are good to go. All right, so now let's have a look at the shape of an original image versus our new image. So I mean, this was just to prove that essentially our original shapes were like 262, 409 by some random values, and they're all reshaped now to 160, 160 by 3. 3 obviously is the color channel of the images. All right, so picking a pre-trained model. So this is the next step. This is probably one of the harder steps, is picking a model that you would actually like to use the base of. Now we're going to use one called MobileNet v2, which is actually from Google. It's built into TensorFlow itself. That's why I've picked it. And all we're going to do is set this. So essentially we're going to say the base model in our code is equal to tf.keras.applications.mobilenet-v2, which is just telling us the architecture of the model that we want, and we'll have a look at it down below here in just a second. We'll define the input shape, which is important because this can take any input shape that we want. So we'll change it to 160, 160 by 3, which we've defined up here. Include top, very important, means do we include the classifier that comes with this network already or not? Now in our case, we're going to be retraining parts of this network so that it works specifically for dogs and cats and not for 1,000 different classes, which is what this model was actually aimed to do. It was trained on 1.4 million images for 1,000 different classes of everyday objects. So we're going to not include the top, which means don't include the classifier for these 1,000 classes. And we're going to load the weights from what's called ImageNet, which is just a specific save of the weights. So this is the architecture, and this is kind of the data that we're filling in for that architecture, so the weights, and we'll load that in, which we have here. So base model, now let's look at it. So let's have a summary. You can see this is a pretty crazy model. I mean, we would never be expected to create something like this by ourselves. This is, you know, teams of data scientists, PhD students, engineers, whatever, right? The experts in the field that have created a network like this. So that's why we're going to use it, because it works so effectively for the generalization at the beginning, which is what we want. And then we can take those features that this takes out. So in 5 by 5 by 1280, which is what I want us to focus on, the output of this actual network here. So out ReLU, you can see this last layer. We're going to take this and using this information, pass that to some more convolutional layers and actually our own classifier, I believe, and use that to predict versus dogs versus cats. So at this point, the base model will simply output a shape 32 by 5 by 5 by 1280. That's the tensor that we're going to get out of this. That's the shape. You can watch how this kind of works as you go through it. And yes. All right. So we can just have a look at this here. This, what I wanted to do essentially was just look at what the actual shape was going to be. So 32 5 by 5 by 1280, just because this gives us none until it knows what the input is. And now it's time to talk about freezing the base. So essentially the point is we want to use this as the base of our network, which means we don't want to change it. If we just put this network in right now as the base to our neural network, well, what's going to happen is it's going to start retraining all these weights and biases. And in fact, it's going to train 2.257 million more weights and biases, when in fact we don't want to change these because these have already been defined, they've been set, and we know that they work well for the problem already, right? They worked well for classifying 1,000 classes. Why are we going to touch this now? And if we were going to touch this, what's the point of even using this base, right? We don't want to train this, we want to leave it the same. So to do that, we're just going to freeze it. Now freezing is a pretty, it just essentially means turning the trainable attribute of a layer off, or of the model off. So what we do is we just say base model.trainable equals false, which essentially means that we are no longer going to be training any aspect of that, I want to say model, although we'll just call it the base layer for now, or the base model. So now if we look at the summary, we can see when we scroll down to the bottom, if we get there any day soon, that now the trainable parameters is 0 instead of 2.257 million, which it was before. And now it's time to add our own classifier on top of this. So essentially we've got a pretty good network, right? 5 by 5 by 1280 is our last output. And what we want to do now is take that and we want to use it to classify either cat or either dog, right? So what we're going to do is add a global average layer, which essentially is going to take the entire average of every single, so of 1,280 different layers that are 5 by 5, and put that into a 1D tensor, which is kind of flattening that for us. So we do that global average pooling, and then we're just going to add the prediction layer, which essentially is going to just be one dense node. And since we're only classifying 2 different classes, right, dogs and cats, we only need 1. Then we're going to add all these models together. So the base model, or not, I guess layers, the global average layer that we defined there, and then the prediction layer to create our final model. So let's do this. Global average layer, prediction layer, model. Give that a second to kind of run there. Now when we look at the summary, we can see we have MobileNet v2, which is actually a model, but that is our base layer, and that's fine because the output shape is that. Then global average pooling, which again just takes this, flattens it out, does the average for us. And then finally our dense layer, which is going to simply have 1 neuron, which is going to be our output. Now notice that we have 2.259 million parameters in total, and only 1,281 of them are trainable. That's because we have 1,280 connections from this layer to this layer, which means 1,280 weights and 1 bias. So that is what we're doing. This is what we have created now. This base, the majority of the network has been done for us, and we just add our own little classifier on top of this. And now we're going to feed some training samples and data to this. Remember, we're not training this base layer whatsoever, so the only thing that needs to be learned is the weights and biases on these 2 layers here. Once we have that, we should have a decent model ready to go. So let's actually train this now. I'm going to compile this here. I'm picking a learning rate that's very slow. What the learning rate means is how much am I allowed to modify the weights and biases of this network, which is what I've done. Just made that very low because we don't want to make any major changes if we don't have to, because we're already using a base model that exists, right? So we'll set the learning rate. I'm not going to talk about what this does specifically. You can look that up if you'd like to. And then the loss function will use binary cross entropy just because we're using 2 classes. If you're using more than 2 classes, you would just have cross entropy or some other type of cross entropy. And then what we're going to do is actually evaluate the model right now before we even train it. So I've compiled it. I've just set what we'll end up using, but I want to evaluate the model currently without training it whatsoever on our validation data, our validation batches, and see what it actually looks like, what it actually, what we're getting right now with the current base model being the way it is, and not having changed the weights and biases, so they're completely random from the global average pooling and the dense layer. So let's evaluate, and let's see what we get as an accuracy. Okay, so we can actually see that with the random weights and biases for those last layer that we added, we're getting an accuracy of 56%, which pretty much means that it's guessing, right? It's, 50%, there's only 2 classes, so if we got anything lower than 50, like 50 should have been our guess, which is what we're getting. So now what we're going to do, and I've trained this already, I think, so I might not have to do it again, is train this model on all of our images, so all of our images in cats and dogs that we've loaded in before, which will allow us now to modify these weights and biases of this layer, so hopefully it can determine what features need to be present for a dog to be a dog and for a cat to be a cat, right? And then it can make a pretty good prediction. And in fact, I'm not going to train this in front of us right now because it actually takes close to an hour to train, just because there is a lot of images that it needs to look at and a lot of calculations that need to happen. But when you do end up training this, you end up getting an accuracy of a close to 92 or 93%, which is pretty good considering the fact that all we did was use an original layer, like base layer, that classified up to 1,000 different images, so very general, and applied that just to cats and dogs by adding our dense layer classifier on top. So you can see this was kind of the accuracy I had from training this previously. I don't want to train again because it takes so long, but I did want to show that you can save a model and load a model by doing this syntax. So essentially, on your model object, you can call model.save, save it as whatever name you like, .h5, which is just a format for saving models in Keras. This is specific to Keras, not TensorFlow. And then you can load the model by doing this. So this is useful because after you train this for an hour, obviously you don't want to retrain this if you don't have to actually use it to make predictions, so you can just load the model. Now, I'm not going to go into using the model specifically. You guys can look up the documentation to do that. We're at the point now where I've showed you so much syntax on predicting and how we actually use the models. But the basic idea would be to do model.predict, right? And then you can see that it's even giving me the input here. So model.predict, give it some X, batch size, verbose, right? Because it will predict on multiple things, and that will spit back to you a class, which then you can figure out, okay, this is a cat or this is a dog. You're going to pass this, obviously, the same input information we had before, which is 160 by 160 by 3. And that will make the prediction for you. So that's kind of the thing there. I was getting an OS error just because I hadn't saved this previously, but that's how you save and load models, which I think is important when you're doing very large models. So when you fit this, feel free to change the epochs to be something slower if you'd like. Again, right, this takes a long time to actually end up running. But you can see that the accuracy increases pretty well exponentially from when we didn't even have that classifier on it. Now, the last thing that I want to talk about is object detection. I'm just going to load up a page. We're not going to do any examples. I'm just going to give you a brief introduction because we're kind of running out of time for this module, because you can use TensorFlow to do object detection and recognition, which is kind of cool. So let's get into that now. Okay, so right now I'm on a GitHub page that's built by TensorFlow here. I'm going to leave that link in the notebook where it said object detection so you guys can look at that. But essentially, there is an API for TensorFlow that does object detection for you. And in fact, it works very well and even gives you confidence scores. So you can see this is what you'll actually end up getting if you end up using this API. Now, unfortunately, we don't have time to go through this because this will take a good amount of time to talk about the setup and how to actually use this project properly. But if you go through this documentation, you should be able to figure it out. And now you guys are familiar with TensorFlow and you understand some of the concepts here. This runs a very different model than what we've discussed before. Unfortunately, again, we don't have time to get into it, but just something I wanted to make clear is that you can do something like this with TensorFlow, and I will leave that resource so that if you'd like to check this out, you can use it. There's also a great module in Python called facial recognition. It's not a part of TensorFlow, but it does use some kind of convolutional neural network to do facial detection and recognition, which is pretty cool as well. So I'll put that link in here, but for now, that's going to be our, convolutional neural network kind of module. So I hope this has cleared some things up on how deep vision works and how convolutional neural networks work. I know I haven't gone into crazy examples, but I've shown you some different techniques that hopefully you'll go look up kind of on your own and really dive into, because now you have that base kind of domain knowledge where you're going to be able to follow along with the tutorial and understand exactly what to do. And if you want to create your own model, get enough sufficient training data, you can load that training data into your computer, put that in a NumPy array. Then what you can do is create a model like we've just done using even something like the MobileNet, V2 that we talked about previously. If I could even get up, I need to close this output. Oh my gosh, this massive output here. Where is this? Picking a pre-trained model. Yeah, MobileNet V2, you can use the base of that and then add your own classifier on, do a similar thing to what I've done with that dense neuron and that global average layer, and hopefully you should get a decent result from that. So this is just showing you what you can do. Obviously, you can pick a different base layer depending on what kind of problem you're trying to solve. So anyways, that has been convolutional neural networks. I hope you enjoyed that module. Now we're on to recurrent neural networks, which is actually going to be pretty interesting. So I'll see you in that module.